Assalamu alaikum students. Today I'm going to discuss about the circular motion. This is the starting topic of your A levels 2 physics. Most of the times a question is asked from gravitational motion, gravitational fields along with the circular motion concepts. That's why it's important to know the gravitation, the concept of circular motion, right? In circular motion, actually, when we consider that an object is moving in a circular path or a curved path, then its motion is considered to be circular motion. But here in our syllabus, that motion is the motion of an object with uniform speed. Okay, so the important thing, when an object is moving with uniform speed in a circular path, we will consider that its motion is considered to be circular motion, uniform circular motion. So in this type of motion, the object is moving with constant speed all the times, but as its direction is changing, that's why it is causing a change in velocity, and due to change in velocity there will be an acceleration in it, and that would lead us towards a constant force acting on the body, which is called your centripetal force. So there is a complete journey from starting point of circular motion to the application area of the centripetal force. So I'm starting with this. I hope that it will help you out. It's very brief and precise lecture. Instead of getting all details, I tried my best that I can provide you a quality stuff in the shortest possible time. So here, let's start with this, that if I have an object of mass m here that is moving in a circular path with uniform speeds. I have not mentioned the direction of the speed, but it can be in any direction. For example, here it would be perpendicular speed of that object all the times. So that object is at a distance r from the center of that circular path, so definitely radius is involved in this motion. So as this object moves on the boundary of the circular path, it covers an arc length, or it travels the distance which is called arc length over here. And meanwhile, there is a change in the displacement or angular displacement which is called theta. So I have mentioned three diagrams over here. In diagram number 1, arc length is very small. That's why theta is small. As arc length increases in diagram number 2, right, arc length increases as the angular displacement increases. Similarly, in your diagram number 3, the arc length becomes equal to half of the circumference of the circle. Similarly, angular displacement has increased to half of the angle subtended at the center of the circle, which is almost equal to 180 degree. We are um, familiar with this concept. So let's talk about the angular displacement in detail. Angular displacement is the displacement of angle, or the angle subtended at the center of the circular path due to motion of a body in a circular path. So mathematically, if I say that as arc length and this angular displacement are proportional to each other, so I can say that s is proportional to the angular displacement, which tells me that if I keep r constant, then my equation holds valid. So s equals to r theta tells me the definition of angular displacement, which is ratio of arc length to the radius of the circle. That is called angular displacement, right? Its definition is radian, which is sorry, its unit is radian, and we are asked to define radian in exam for 2 marks, and that is the angle subtended at the center of the circle when arc length becomes equal to radius of the circle. So 1 mark is awarded over here, 1 mark is awarded over here. So by that, I can say mathematically that theta is equals to s divided by r. So if I consider that there is a change in angular displacement, then definitely there is a change in arc length, but not in the radius. So this is first aspect of your circular motion. I hope that it would be very clear to you. Now I'm going to move to the next aspect of the circular motion, that is the calculations or calculative area of the circular motion. It's how to relate the units of circular motion, the angular displacement, which are commonly used in our daily life. So overall, this topic is called kinematics of circular motion, because I will talk about this angular velocity and all that stuff. Here we are known to this fact that for one complete revolution, the angle subtended at the center of the circle will be equals to 360 degree, which is equals to 2 pi radians. So 1 degree is equals to 2 pi by 360 radian. It means 1 degree equals to pi by 180 radians. This gives very clear relation between degree and radian, that if I want to measure 1 radian is actually 180 divided by pi degrees. So this is very important relation, very important relation, which is mostly used for the conversions, that 1 radian equals to 57.3 degrees. Okay, so if I would not be mistaken, it is really closer to 60 degrees. So because 60 degrees is very easy to visualize, and in physics, if you are going to visualize something, you are very much clear about the concept. So 1 radian is approximately 60 degrees, right? Two-third of a quadrant to somehow. Now let's talk about angular velocity or angular speed. As I told you that this topic is actually the kinematics of circular motion. That's why here I'm talking about the angular velocity. Angular velocity is basically rate of change of angular displacement. Here the angular displacement was delta theta and time is t. So if I say that there is a change in angular displacement, it means that I can have delta theta divided by time, which is giving me a new physical quantity, which is angular velocity. So its unit is radian per second. So I can write radian per second over here. Usually it is r rad second minus 1. So for one complete revolution, your angular displacement is 2 pi radian. It is mentioned over here. And time period is t, or time taken is equal to one time period. That's why when I write, when I substitute these specifications actually in my general equation, which is 2 pi by, which is delta theta divided by t, then it becomes 2 pi by t, because delta theta is your 2 pi radians, and time is one time period. That's why it becomes omega is equals to 2 pi radian. This is very important equation for you. It has a long existence in your syllabus. For example, it would be asked in gravitational topic, it will be asked in oscillation topic. Then there are so many, for example, where we are including waves. This question, this equation is basically used over there as omega is equals to 2 pi by t. Now as we know that in this equation 1 upon t is hidden, so 1 upon t is frequency. So I have the linear formation of this equation, that omega is equals to 2 pi f. So simply speaking, I have two equations of omega. One is omega is equals to 2 pi by t, and the second one is 2 pi f. These two are very common equations. Please remember these equations for your further topics. As I told you, oscillation, capacitance, and all that stuff. Now, there is another important aspect of angular speed, that is revolutions per minute or revolutions per second. Number of revolutions per minute. Normally, it is called RPMs. So, if I say that the speed is measured into RPMs, the RPMs mean revolutions per minute. So, number of revolutions per minute means how many times 2 pi radians have been covered. So if I say that 2 pi radians divided by 60, because time is into minutes and minute is converted into 60 into seconds, so it is 2 pi by 60 radians, radians per second. So here I'm going to make it simple for you people. One revolution per minute mean your angle has been subtended at the center of the circle for 22 pi radians in 60 seconds. So it becomes 2 pi radians by 60. Or simply speaking, when we are going to convert RPMs to radian per second, multiply the value of RPM, whatever the value of RPM, multiply this by 2 pi by 60. With which number? 2 pi by 60. So you will get the unit in radian per second. So sometimes this question is asked to you, that's why I have considered that. So this is that concept. Whatever the value or whatever the number of revolutions are given to you, multiply that by 2 pi by 60, you will get revolutions per second converted into radian per second. I hope that this slide is clear to all of you. Now I will move to the next slide of my topic, and that is basically covering the precise concept of angular velocity and its calculations. Now, here I have considered some calculation areas of the angular velocity. The very important and common example for angular velocity calculation is your clock. Clock has three arms: second arm, minute arm, and an hour arm. So if I want to calculate, or if I want to measure the